Okay, so this is why I said we're going to kind of work backwards on the lab. So you've got that free response question straight off of an old AP exam. So part of this, and this is what I just showed you. So we had the oscillator, okay, which was the thing going up and down. You had a string, you had a weight hanging from the end of the string. Okay, so this is the exact same setup that I just showed you. So with this one, he's got frequency, vibrates in the second harmonic. So again, this is, you understand the difference between the first harmonic and the second harmonic. So if it was the first harmonic, here's your length, what would that look like if it was just the first harmonic? You'd have one antinode and two nodes. Okay? That's if it was the first harmonic. So the second harmonic is going to have, so that's just going to go something like that. Okay? That's it. And then it says, label the points on the string that have the greatest average vertical speed. Well, what do you think the average speed of the nodes is? 0. So what do you think has the highest velocity? The antinode. Okay, so you go. So then on those questions, so let's kind of go through those on this setup. So part of this is figuring out what's the same and what is changed between these systems. So you're told that the same mass at each block is the same. So you've got this setup, and this is like looking down from on top, so you kind of have to visualize what this is looking at. So you're looking down from on top, and that's why it has like that pulley like this, and then the string, and then you have mass. So this is not like the sideways view. This is looking down from on top. So you look at that equation, you have V equals the square root of Ft over M over L. You're used to seeing that as tension over mu, and mu is the same thing, which is that mass per unit of length. Okay? It's the same thing. So what's the difference about the four strings? The result of having different fundamental frequencies. Okay, so again, you have two ideas here. If you look at this, they have the same mass hanging from the end of the string. So if they have the same mass hanging from the end of the string, they're going to have the same tension. Okay, that's the same. The L is the same because it's the same length. So it's the only thing that can create the difference. The mass per unit length of the string. Okay? That's why if you look at a guitar or a banjo, you have different size strings. You have some that are very small and you have some that are much bigger. So, what's the relationship? Is there a direct or direct with the square root relationship between tension and velocity? Direct with square root. Okay, it's not a simple direct relationship. Why? It's underneath the square root function, right? So here's what you should be able to do. If I want to double the velocity, assuming that the mass per unit of length stays the same, this is what you should be able to think through at this point. If I want to double the velocity, what should I do to the force or the tension that's on the string? Increase it by 4. What? Square root, right? So if I increase the tension by a factor of 4, I'm going to double the velocity. Now, what else does velocity equal? Lambda times frequency. Okay? So if I double the velocity, something has to change over here. Right? Something has to change over there. Either I increase my wavelength, I increase the frequency, something has to change to create that higher velocity. Now, common misconception. This V is not the velocity of sound. Okay? This is not the sound that's being produced. This is the velocity on the string. Okay? It is not the speed of sound. Okay? It's the velocity of the wave on the string. So if I double the velocity, maybe I double the wavelength, maybe I double the frequency. It depends upon what's going to stay constant within the confines of that system. Okay? All right. So when you get to A, what is different about the four strings shown above that would result in their having different fundamental frequency? Now, when it says explain how you arrived at your answers, okay? Just don't say, oh, they're different. That's why. No help. You want to explain your thought process. You might want to explain what's the same, because you want to explain the thought process. So you might want to say what's the same and what has changed to create that difference. Okay?
So if I were to say the tension is constant and the length is constant, so the only other thing that can change it is the mass per length unit thing?
That couldn't be better.
Well, you didn't actually know that. You just said like.
Did you write like a thesis?
It's at least 30 words.
Okay.
1, 2, 3, 4, 5.
Maybe.
Okay. Now, when you get to B, student graph's frequency is a function of the inverse of linear mass density. Would the graph be linear? Absolutely not. Why? What's the only way you could? What's the only way it could be linear? Is if it was in the form of y equals mx plus b. Does that look anything like a linear function? No. Okay? Absolutely not. There is nothing in there that's linear. Now, but let me give a caveat where it could be linear. Okay? It's not, but let's just say. Let's say that you have velocity equals the square root of force tension over mass. Okay? I'm going to change this. Okay? This is not the equation, but I want to show you where it could be linear. And then you multiply that by L. Okay? Now, this could be a linear function. This would be your y value. This would be your x value. And this would represent your slope. That could be a linear function. But this whole thing would represent the slope of the line. And you would have to keep the force tension and the mass the same. Then it would be a linear relationship between length and velocity. So if that L was on the outside, that could be a linear function. But it's not. So that's why it's not a linear function.
By the way,
Okay?
my part A is 34.
Okay. My answer is 22. Mine's 10.
10 on what?
My answer.
Answer to what? Wait,
Oh.
numbers now? No, just how many words?
Make sure on your graph, and some of your graphs look kind of different, but main idea. So you have frequency here, and you have 1 over wavelength here, which are not the same thing, are they, David?
Nope.
Half mine's not even here. Never mind. Who asked? You asked about it. Shannon, you asked about it yesterday.
I didn't get my question out before I retracted my statement.
Oh, you said it before you retracted it.
Is that my down the entire block?
Yeah.
Yeah.
Well, theoretically, if it's
Okay.
and they said
So, this is where you have to look at the units. What's frequency going to be in?
Hertz.
Hertz are 1 over second. This is 1 over wavelength, which is going to be 1 over. You're going to have a line that's going to look like this. Slope is changing y over. So your y's have units of 1 over. This is 1 over meters. So you end up with.
Is that right? That's what he said.
I'll show you around.
It is around 340.
Yo, yours is
Yeah.
3.2.
Is it?
Okay, on
Right.
page 2, where you're showing like the 0.3 B, the L, I don't need to see every calculation, but I need to see one good set of calculations. Okay? I don't need to see them all, but I want to see one clear set of calculations Okay?
Can you stop, please?
Different percent.
One clear set.
Thank you.
An entire 0.1 difference.
On that unknown, you're going to use as the accepted speed of sound what we calculated yesterday, which was basically 43. And then I want to see how you arrived at that frequency. That frequency should probably be around 430
Wait, hold on.
on the unknown. Around.
It should be around what?
Around. If you have 800, that's bad.
Do you think mine sounds good? I feel like it's so obvious that we experienced that.
That's what I.
Yeah.
I just put
Wait, for
the
the-
word
What?
Air Markle was illegal.
Yeah, I think so.
Huh?
Air Markle was illegal.
Mine
It just sounds so straightforward. Since these
I
don't
would use
change.
the furthest point, which would be
That's what
the 5, 12. So.
What do you want me to say?
Oh, but I just, mainly because try and find the element air.
This is okay, this is unstable. Okay, but if you look at the medium table, it says air.
I don't care. People also use the word decelerate.
Yeah.
Okay?
Mr. Burns.